Hi, I'm Daniel Bolia, and along with my co-authors Rohit Mittapalli and Judy Hoffman, we're happy to present Scalable Diverse Model Selection for Accessible Transfer Learning this year at NeurIPS. It's no secret that today's deep models take a massive amount of data and resources to train. That's why many choose to employ transfer learning rather than training from scratch. The most popular method to do this today is to take a model that was trained on a large dataset and fine-tune it for your own, much smaller dataset. Doing this is usually much faster than training from scratch and can often be more accurate too. But this process can still be costly. There are several model banks out there with models trained on huge datasets, so getting a pre-trained model is not the problem. Instead, deciding which pre-trained model and dataset to use can be a big bottleneck. Depending on your use case, the standard fare using ImageNet for vision tasks might not perform the best, so you might have to try other datasets. And if you want your model to be fast while retaining acceptable accuracy, you're also going to need to test out some different architectures. Doing all this testing can end up taking a lot of time, and because of this, most don't even bother. Wouldn't it be nice if there were a model selection method that could perform this for you? For such a method to be useful, it would need to be scalable to evaluate quickly on large model banks, and it would need to support a diverse array of models and tasks. In this paper, we attempt to facilitate this by introducing a benchmark and corresponding method for scalable diverse model selection. Our goal here is to be able to select a good pre-trained model for your data from a massive, unconstrained, and diverse set of pre-trained source models, which can span several different datasets, architectures, and tasks. However, such an all-encompassing use case is not well represented in the literature. There have been other methods and benchmarks that try to do something similar, but none meet both the requirements of scalability and robustness to diverse source models. For instance, Neural Data Server can recommend extra data, but not models. They also require training from scratch with that data, which can be a huge time sink. Taskonomy can be used to benchmark model selection, but it uses just one architecture and dataset, and thus can be only used to benchmark transfer across tasks. And there are also several probabilistic methods that try to predict transfer accuracy, but for the most part, they're restricted to classification, and they don't test across architectures. They also transfer from one source model to several target datasets, which is different from our setting where we transfer from several source models to one target dataset. This is a more important detail than you might realize, and we discuss this in the paper. Thus, we've set out to create our own benchmark for this task. This benchmark includes 6 target datasets split into 3 transfer-friendly categories such as pets and birds, 8 source datasets including those 6 target datasets as well as VOC 2007 and the ubiquitous ImageNet 1K. And then finally, 4 different architectures offering 3 tiers of speed, so the speed-performance trade-off can be easily studied. In total, we've trained 168 transfers to test scalable diverse model selection. For ease of comparing existing methods, this benchmark is fixed to be classification, but we have extensions for other tasks if you stick around. In order to measure performance on this benchmark, we ask methods to predict the transfer performance of a given set of source models to a target dataset. Note that here we only give the method a 500 image probe set, not the full dataset, both to ensure faster evaluation and that these methods can operate in low data regimes where transfer learning is likely to be necessary. Finally, we then report how well those model scores correlated with the true accuracy of the transfer models that we trained ourselves, and average across all the different target datasets. We use Pearson correlation here because it's the standard used for transferability. Previous methods tend to fail spectacularly when evaluated on this benchmark. Note that 100 here is the best possible correlation, while 0 means no correlation. NCE and LEAP perform very poorly because of the small probe set, as well as having to compare across different source models. Notably, they also suffer from changing the evaluation criteria from comparing across target datasets to comparing across source models like we do. This fact was very surprising to us, so we encourage you to read the details in the paper. RSA and DDS do well, but they require training an additional model to make this recommendation. And if you choose the wrong architecture, these methods also fail catastrophically. For instance, RSA using Resident 50 does well here, but RSA using AlexNet gets no correlation. Finally, some simple baseline methods, like training a nearest neighbor or logistic classifier on the small 500 image probe set, actually yields better performance than these other methods. Not to mention, some of these methods are slow. Depending on the model used, RSA and DDS can take up to 3 hours of extra training time. And some methods like H-score and the logistic classifier baseline can take multiple seconds per transfer, which can get costly with larger model banks. In the paper, we analyze why all these failures happen in both accuracy and speed, and offer several improvements to fix these issues. Specifically, we add PCI dimensionality reduction to ensure that the source model features are consistent. Furthermore, we add a heuristic to model the source architecture's capacity to learn new information. Depending on the method, these techniques together can provide a significant boost of up to 17% on our benchmark. This leads us to introduce our own method for scalable diverse model selection, dubbed PARC, short for Pairwise Annotation Representation Comparison. We base PARC off of RSA, which computes the similarity between images in the feature space of two different models, one being the source model and the other being a model that was trained on the target dataset. RSA predicts a source model to transfer well if both of these models consider the same images similar. This, of course, requires already having a model trained on the target set, which we'd obviously like to avoid. However, with PARC, we use a simple aggregating function specific to each task to create pseudo-features from the labels. These pseudo-features then can be used to create the similarity matrix used for transferability estimation. PARC outperforms every other method, even when each method is given access to all the same beneficial techniques. Moreover, it's one of the fastest methods due to its simplicity. It also doesn't have any restrictions on requiring extra models or only working on certain tasks, as long as a simple aggregating function can be defined. We also extend our benchmark to test more scenarios, and PARC excels there as well. We create a crowdsourced benchmark that includes 423 transfers comprised of off-the-shelf models downloaded from model banks. While this is a much harder task, PARC still outperforms every other method, indicating that it's very robust to diverse source models. We also show its capability of extending to different tasks by collecting an object detection benchmark, where it does comparably to RSA but without the 12-hour training time cost. We'll be making at least the main benchmark suite available on our GitHub link here, and hope we can help facilitate further advances to the task of scalable diverse model selection. Thanks for listening.